All right, picking up where we left off. So we've got this scatter plot with just two pieces of data. There's one down here. The x-coordinate is 1.1, the y-coordinate is 2.3. And there's one up here where the x-coordinate is 3.6 and 4.9. And I asked, do we think these two quantitative variables have a correlation? The answer is yes, they do. In fact, they have a perfect correlation of 1. And the reason for that is with just 2 points, you can always draw a line connecting those 2 points. Of course, as statisticians, we know that 2 points is not enough data to make a conclusion. So the correlation between two quantitative variables, it can be there for lots of reasons. The question is it actually meaningful? Is it statistically significant? And is it practically significant? So every correlation should contain a hidden hypothesis test. So let me talk through what that hypothesis test will look like. All right. So the hidden hypothesis test or a correlation. Our research question is, are the two variables correlated in a statistically significant manner? Your null hypothesis is no, they are not. Right? It's just random. Any correlation we see was random. And the alternative is yes, they are correlated. The correlation that we see is actually statistically significant. For a significance level, nobody tells you otherwise. Let's choose 0.05. We collected our data. Our data here is pretty sparse. We just have our two data points. So we've collected our data. X is 1.1 and 3.6. Y is 2.3 and 4.9. And actually, one thing is we can't actually do a correlation test. We can't do a hypothesis test on just two data points for the specific reason that you can always connect it with a line. So if we're going to do a hypothesis test, we actually need at least 3 points of data. So there's our third point of data. It's X is 2 and Y was 3. And then we can actually calculate the p-value, or I guess we do our summary statistic next, which is a correlation. The correlation of these two variables was 0.99. It was no longer 1 because these 3 points don't lie on a perfect line, but it sure is very close to a perfect line. So we have a very high correlation. But now we ask, how likely is it that this correlation was just due to chance, in particular due to having a very small amount of data? So the way we do that in R is we use core.test. So if we run core.test, there's our correlation again, 0.99, but there's our p-value, 0.606. So when we do our hypothesis test, we do core dot test of x comma y, and the p-value is 0.06, which is larger than 0.05. And that tells us that this correlation that we calculated could have been due to random chance, and we failed to reject the null hypothesis. We conclude that we don't have enough evidence because we didn't collect enough data. We don't have enough evidence to say there is truly a correlation. Now let's compare that correlation with just three data points to the correlation between our iris petal length and our iris petal width. So instead of just correlation, we'll do core dot test. Let's look at that plot again. They sure seem pretty correlated. And when we do core dot test, we see that the correlation is 0.96. And the probability of observing that correlation through random chance is 2.2 times 10 to the minus 16. That's basically 2.2 divided by 10 quadrillion, something like that, basically zero. So the probability of observing this correlation due to random chance is basically zero. So we can conclude that yes, there definitely is a correlation between these two quantitative variables. All right. So it's time to talk about the second set of summary statistics when we are comparing or exploring the relationship between two quantitative variables. And this is what brings us finally to simple linear regression. The second set of summary statistics for um, exploring the relationship or association or correlation between two quantitative variables is called a linear regression, sometimes called a linear regression model or a simple linear regression, lots of different words that statisticians have used for this idea. But here's the basic idea. We've got our data. Here's our iris data with length here and width here. And there's our data. Sure looks like it's correlated. We've done a correlation test and we've quantified the correlation, but it would be nice to know what the actual relationship is between length and width in centimeters. For example, if we knew what this length was, it would be nice to have an idea about what that width would be. And the correlation doesn't tell us that. The correlation just tells us that they're related, but it doesn't tell us how. A linear regression model tells us how two quantitative variables are related. If I were to draw a line that goes through this data as best as possible, I would probably draw this line. That's pretty good. Maybe not perfect. But this line is close to all the data points, and we call this the line of best fit. And a linear regression model is simply the equation of this line. So any line can be described with the equation y equals mx plus b, where m is the slope and b is the y-intercept. The y-intercept is where that line would cross the vertical axis, and the slope is the change in the y as the x changes. The slope is how the output changes as the input changes. And the y-intercept is the y value when x equals 0. So let's hop back to R and actually do that calculation from within R. So here's my data, and I would like to be able to plot the line of best fit. And to do that, I'm going to use this command lm, which creates a linear model. And I'm going to say I want to predict the petal width of irises if I know the petal length of irises. And with that, I can draw my line of best fit. So this is mathematically the line that best fits the data. It minimizes all of these little differences between the actual observations and the line representing the trend of these observations. And if I want to see the values, I can use summary of the linear model, and it's going to show me these values here. That will end this video. The next video will pick up and close out this lecture on linear regression.